All right, welcome back. Guys, things are about to get real. We spent the first half of this course talking about differential calculus, derivatives. We've just spent most of this chapter talking about integrals, area under the curve, and we're about to put them together and connect them. So what have we done so far? Thing one, we used a program, numeric integration, to find the values of integrals. Fair enough, pretty easy. Type them into the calculator, boom, we've got an answer. Thing two, we used area to find the values of integrals. Again, simple enough. Hey, look, there's a circle. Geometry says, boom. You guys who just finished watching my last video are now laughing at me, but that's okay. I'm all right with it. We've also had some given values. For example, we were given that the integral from 0 to pi of sine of x dx was equal to 2. Well, the question is, how do we know this? Now, we could make the argument that, well, we know it because we shoved it into our calculator and it said 2, but how do we know that 2 is correct? And how do we know that that's accurate given that the calculator is just doing an approximation? It's doing a rectangular approximation. And how did they know this before calculators? Did they just calculate every single rectangle and add them together? So we're going to talk about this, and we're going to start with an exploration. And we are going to look at just some random function that looks like this. And it runs from A to B. And we're going to pick some random value of x, and we're going to draw all of our little rectangles in. So we can agree that the area I just shaded is the integral from a to x of this function, f of t dt, and that this is an accumulator function. And again, if you're not sure what I'm talking about, you might want to go back and watch the previous chapter videos where we talked about accumulator functions. We're just adding up, we're accumulating all of these little rectangles between a and x. And we're going to refer to this accumulator function as capital F. F of x, the accumulator function, is the area under the curve from a to x, also known as the integral from a to x of f of t dt. All right, and this function is y equals f of t. All right, so let's think about derivatives. If I want to take the derivative of f with respect to x, I could say that it is the limit as the change in x goes to 0 of change in f over change in x. Again, notice uppercase because we're talking about our accumulator function. So I'm going to draw one more rectangle, and I want it to be in this. I'm going to draw one more rectangle right there. I've added one rectangle to the end of my derivative. And if I sketch out this rectangle down here, I actually prefer a thinner pen, I know that the width of this rectangle is delta x. And I know that the height of this rectangle is f of something in the middle of my function. So we'll say f of x. Remember that x was right here, and this is x plus delta x right here. And I know that the area of this rectangle is the change in my accumulator function. So what that means is that the change in my function is equal to the height times the width, which means that the height of my function f of x is equal to the change in the accumulator over the change in the width. But that tells me that this right here, the derivative, is equal to the limit as delta x goes to 0 of my function. But what's my function equal to as delta x goes to 0? Well, delta x going to 0 is completely and utterly irrelevant when it comes to the value of my function. It has nothing to do with it. The value of my function is the height of that rectangle. It doesn't matter how wide the rectangle is. So what I now see here is that the derivative of my accumulator function is just the original function. And what this tells me is that the derivative and the integral are inverse functions. And we call this, we say that the integral is an antiderivative of the function. So how can we use this? Well, let's dive in a little bit further. We now know that f is, oops, change colors. F is an antiderivative of f, which means that the integral from a to x of f of t dt must be equal to the antiderivative plus a constant. Remember the plus a constant. When I take the derivative of f plus a constant, well, the derivative of the constant is 0, and I get the derivative of f. So let's do a little mathematical trickery. Let's talk about the integral from a to a of f of t dt is equal to f of a plus a constant. But I know that this is equal to 0. And what that tells us is that my constant is equal to the negative of f of a. Let me back up just a second. We all comfortable that that's equal to 0 because the width of our interval is 0, which means that the area must also be 0. All right. So what we now have is that the integral from a to x of f of t dt is equal to the antiderivative at a, the antiderivative at x, got ahead of myself there, minus the antiderivative at a. So this would be a good thing to copy down into your notes, and let's do a very quick example of how we use this. Let's find the integral from 0 to pi of sine of x dx. Well, we know that the antiderivative of sine is negative cosine. Let's back up just a second here. Let's make this x. So this will be negative cosine of x minus, this is f of x, the antiderivative, minus f of a, well, minus the negative cosine of 0. So now let's make x equal to pi. this becomes the negative cosine of pi plus the cosine of 0. Hopefully we remember from geometry that the cosine of 0 is 1, the cosine of pi is -1, so this becomes the negative of -1 plus 1, which is equal to 2. And wow, look at that. We have just shown that the integral from 0 to pi of sine of x dx is equal to 2. In other words, the area under that curve right there is equal to 2. All right. Those of you in my class, go ahead and do exercise 21, a little quick practice, and we'll be back with more. Thanks for watching.